At the schedule, and I don't see any way where we could get the stuff on homework 4 covered early enough such that we'd be ready for the first midterm on the Tuesday before you go on spring break. So it's looking like the exam will have to be on Thursday. I know that was the OChem date, but unfortunately I don't know that there's anything we can do about it. As a reminder, we have a 2-week gap following the that exam, so I don't think you would want it after we come back, right? Okay, so we're going to have to deal with it being on the same day as another exam. If you want, you can pretend it's on Tuesday and study for it like it's on Tuesday. It's not like memorization heavy, so you can then, you know, whatever mental trickery you need to do. So I'll do my best to avoid OChem on my second midterm, and that will have a little bit more wiggle room to do so, because if the date that we would otherwise have it is going to fall on that exam, I can delay it by 1 lecture, and then there's no big penalty for that. So, so that's kind of just a little taste of looking forward here in the next couple of weeks. Any questions or anything before I start? Okay, so in order to finish off what's on your homework number 3, I want to do a big combo circuit, give you some tools and strategies for doing one of those. And then we'll talk about a little bit about measurement devices, voltmeters and ammeters, and that'll close things out. So here's going to be an example of a combo circuit. Doesn't really matter what it is, but we want to be able to tackle a more complicated circuit. Just make one. I'm purposely making it weirdly shaped because circuits don't always look like they're in boxes and rectangles, so I made a triangle. And the wires aren't all bent into 90-degree angles. If you do that, your lab instructor will probably be upset with you because it'll wear them out faster. So it's really good to make a connection between the boxy circuits that you see in class and the actual circuits that you see in the lab. Let's give some values. My battery is going to be 12 volts. So that sets a 12-volt journey from top to bottom. And let's go ahead and label these resistors R1, R2, R3, R4. And I'll just give them some values. 20, 40, 80, 30. And I'm just going to ask, what is the current through each resistor and what is the voltage through each one? So let me give you some like problem-solving strategy for attacking this. Problem-solving strategy for combo circuits and anything complicated, more complicated like this. So my first piece of advice is to identify the equipotential plateaus. Basically the plateaus of voltage that you're going to be moving in between when you have current flow through the resistors. So the highest voltage equipotential is always the one that is connected to the high voltage terminal of the battery. So there's my A. And then the lowest voltage equipotential is always the one with the low voltage terminal of the battery, and you just circle whatever contiguous piece of wire is connected to it. A weird break in the circuit. Let me make sure to put that in there. Okay? And you can label that whatever letter you want. I'm going to label it D. Of course, because I already know how many there are going to be, and I want them to be lettered in order. So let's take a look at the other segments. we have one section of equipotential right here. There's no resistors in there. It's just a contiguous piece of wire. And I have another one that's right here. So my first step in the problem-solving strategy is to circle your equipotential regions. And once you have done that, you can rank them in order from highest to lowest, and that will establish what direction the current flows are. So then you rank them from high to low and identify the current flow directions. So this region right here, this is obviously going to have to be lower than region A, because if it wasn't, why would any current flow out of region A? Because the only place it has to go to is this region. I guess I'll label it B. Why would any charge, its only option to get from A to anywhere else is B, so B is going to have to be a lower voltage, okay? So current flows through resistor 1 from region A to region B because there's lower voltage to be found there, okay? So now we're in region B. Region B, the charges can't just pile up there. They're not done, so they have to have access to lower voltage from there to continue to flow. The current would never flow if it just found it had a dead end. It's got to have access to the lowest voltage region. One way it can do that is by going directly through resistor 2, and then it's already at the lowest voltage region. Or the other option, if it's in region B, is it can split off and go into region C. Region C has to be lower voltage than B, so this is I3, I'll call it. And then C still has to be higher than D, because otherwise charges would not want to continue to flow. They'd be pooling up in C. So I'll call that I4. So just like that, I've established what are all the voltage rankings and what are the current flows. At this point, I might recommend that you draw yourself, I don't know how many steps you want to break this into, I guess, draw yourself a nice voltage waterfall to organize your information. Remember that the higher you are on the page, the higher the voltage is. So you can kind of think of the battery as a pump that recirculates. And then once you're at the top, you only have a single option, resistor 1, where you have to go through resistor 1 to drop down from region A to equipotential region B. Once you're in equipotential region B, you have several options. You can either choose to drop all the way down to D, which is the end of the line, and that's through resistor 2. Or you could split off and join and go through resistor 3, and then continue through resistor 4, along the way having a pit stop at region C. So there's your voltage waterfall. You can literally imagine it like some, weird shaped waterfall someone has in their backyard for decoration, okay? So you have the top tier here, then the water splits off, some of it goes directly down to the bottom, and then or you could take a two-stepper to get to the bottom, okay? So this is going to be helpful for organization as we go through. So here's the next step. Now that we've established all that, and by the way, if you have a single battery, there should never be any ambiguity on the ranking of equipotential regions and the direction of current flow. Okay? You should never get stuck for figuring that out. There will be a logical progression of currents from higher voltage to lower voltage. Okay? All right. So now what we're going to do is we're going to combine things in series and parallel as appropriate. So we have that resistors are in series. The whole idea of a series is that once you committed to going through one, you will go through the other. So there's whatever current passes through both of them, or through one will pass through the other and vice versa. So two things can only be in series if the current is the same. Okay? So once you go through one, you have to go through the other, and if you went through one, vice versa, right? So the two resistors are interchangeable. They have the same current that once you go through one, you have to go through the other. Two resistors are in parallel when their voltage drops are the same. In other words, when they connect the exact same two equipotential regions, they just give you different options on how to proceed between them. Okay? So you're trying to get between the exact same two places, same two equipotential regions. You just can go through this one or through this one. So that's the whole idea of parallel. So what you're going to do is you're going to just crunch this entire circuit down by combining series and parallel elements. There will always be some place to start, but there can be mistakes that get made. So let's take a look at some things that I'll ask you some combinations. You tell me, are they series, are they parallel, or neither? Okay? So let's say take R1 and R3. Series, parallel, or neither? They're neither. Okay? If you go through this one, you don't have to go through this one. You can bounce out over here. Okay? If you go through this one, you don't have to go through this one. All right? So can't combine R1 and R3 in series. All right? Let's do, how about R2 and R3? Are they series, parallel, or neither? Neither. Okay? They look parallel. I know they sort of look parallel. It doesn't have nothing to do with anything. Okay? You can connect the circuit however you want. R2 allows you to jump between B and D. This resistor allows you to jump between B and C. They're not independent. They're not just two choices to get between the same regions. They link different regions. Okay? How about, I don't know, R2, R4? Are they series, parallel, or neither? Neither. Okay, so you can't just start combining things. There's always somewhere to start. There's never going to be a circuit where there's nothing in series or nothing in parallel. But you have to be careful on how you start. Where can I start?
You can put 3 and 4 in series.
3 and 4 in series, that's right. Because once you commit to going through resistor 3, you have to finish going through 4. So every electron that courses through resistor 3 will also go through 4 and vice versa. So that's where I start. I recognize that R3 and R4 are in series. And in fact, that is the only place to start. There is no other starting point. There are no two individual resistors in here that have a series or parallel relationship besides these two. Okay? So one of the things I can realize is that I3 and I4 are the same. Right? I didn't really need to label them differently. I3 and I4 are one and the same. In fact, I might call it R34. It's the current that'll split off to the 3-4 branch. Okay? So I'm going to combine them. If they're in series, I just add them. And when I add them, I'm not going to call it REQ yet because, of course, I'm just one step down the road. I'm going to label the result R34 because the subscript reminds me what all resistors went into that, right? So this is just 3 and 4. So I add those up, and I get, 80 plus 30? 80 ohms plus 30 ohms, that's 110 ohms, right? All right? And especially when you're first doing it, and I would say even in general, it's very helpful every time you combine something, redraw the circuit. So I'm going to redraw the circuit. Let's draw it like this. So this is R1, this is R2, and now this is R34. Okay, I could circle the equipotential regions still. This is, let me not circle them, but let me just label them. This is A. This is D. Those haven't had much change. But now this region is now B. Now you may wonder, well, where did C go? Where's C? Well, C was the middle step that was in the middle of our series circuit, and now what we've done is we've, of course, condensed that series chain into a single resistance. So every time you add resistors in series, you're going to eliminate equipotential regions. So as you're circling around on this, you're basically going to do this over and over again with various resistors. I want you to remember that when you're combining things in series, equipotential regions get deleted, so to speak. Oh, and I guess the other thing that I should mention that I could have done a little earlier, the classic boxy way to draw this circuit would look like this. This is how you might see this in a box shape. So you have region A, you have region B. From B you can jump straight down to D, or you can take a pit stop through C. Now circling the equipotential regions is your way of insulating yourself against getting confused by cosmetic differences. Over here, I had these in a triangle just because I don't know, I just wanted to put them in a triangle. And here they're all boxy shaped. Most of the problems that you'll have in the book, unfortunately, are boxy shaped. And then you get this weird disconnect when you see a circuit in the real world where the wires aren't bent at 90-degree angles. It's, you get all confused. So it's important to not get confused by that. Make sure you understand that whether the circuit cosmetically looks like this or it cosmetically looks like this, it's exactly the same electrically. It's this voltage waterfall. Okay? All right, so sorry I didn't mention that earlier. Let's get back on track. And it's often a lot easier to look at the redrawn graph to figure out what to do next. All right, so I'm looking for series and parallel relationships. R1, R2, is that series, parallel, or neither? Neither, right? They're not in parallel because they don't allow the same jumps. R1 is from A to B, and R2 is from B to D. And also, they're not in series because if you go through this one, you don't have to go through that one. So, what's our next move? Parallel. Now, I can say R2 is in parallel to R34. These are both just different options to jump from B to D. So a charge will either go through R2 or R34. Okay? So now, remember, R2 is not in parallel with R3 alone. What I'm saying is R2 is in parallel with the 3-4 combo, right? So both 2 and the 3-4 combo allow you to jump between regions B and D. There's just two different options to do that. So we go ahead and we say that R2 and R34 are in parallel. And that's because the voltage drop across them is the same. You can also look at the voltage waterfall and see that, right? We have two different ways of connecting regions B and D. Region resistor 2 or the 3-4 combination. All right. So we do our 1 over rule. 1, and the result I'm going to call 2, 3, 4. That's the combo of R2 and R34. All right. So let me put in my values. My two resistances, I have a 40 ohm that I'm putting in parallel with 110 ohm. Now before you work out the math for what R234 is, let me ask you conceptually, is it less than 40, between 40 and 110, or more than 110? It's less than 40, remember. Even if you have just a 40 ohm resistor, if you add an extra branch as 110, that's still better to have it there than not. It makes the system easier to get through. And in fact, if you work this out, you'll get a value of 29 1/3 ohms. If you're doing this, and you're doing this crunching the numbers here, I generally would encourage you to solve symbolically, but these would get really insane if you did that all the way through. I would just encourage you to keep the numbers to at least 3 sig figs so that you don't incur any progressive round off. And there's a warning on the homework about that as well. So here I kept 4 sig figs just to be sure. I'm never going to penalize you for too many, and WebAssign doesn't care either if it's too many, but if you round off too much, you might go outside of whatever its tolerance is. Okay, so that's my circuit. And then I go ahead and resketch it. I have R1 and I have R234. I've condensed the options here. And let me again label my equipotential regions. I have A is the top, I have B is the middle, and I have D is the bottom. Now notice here that there were no equipotential regions missing from the previous line. That's because when you're combining things in parallel, you're condensing the options between the equipotential regions, but the equipotential regions themselves are still there. So when you're combining resistors in parallel, equipotentials are not deleted or condensed. They'll need to. So anytime a series combo comes up, you can expect some equipotentials that you labeled to disappear from the drawing, but in parallel, you don't. They should all still be there. What I've done is I've condensed all of the options from B to D into now a single resistor. All right? So, what relationship do those two have now, R1 and R234?
Series.
They're in series, because if you go through one, you have to go through the other. Which is really our way of saying that if you go through resistor 1, you have to go through the 2, 3, 4 combo somewhere. You have choices within that combo, but you got to go through there somewhere. You go through R1, you have to go through 2, 3, 4. So that's our final combination. We're going to combine R1 and R234 in series. They have the same current. And by the way, that same current is actually the total current, because there are no other branches left. This is actually going to be I total. So let's go ahead and do that, and our result is going to be R equivalent. And then finally, I'm using the label R equivalent because that, of course, is now the actual entire equivalent resistance of the entire circuit. So I add my 20 ohms to, from the previous line, are 29.33 ohms, and I get an overall resistance presented by this circuit of 49 1/3 ohms. Okay? So you basically repeat the process of identifying series and parallel elements until you have R equivalent. You've condensed the entire resistance of the circuit down to a single value. I guess I can draw it here. This is my R equivalent. And once again, because that was a series combo, I've deleted an equipotential region. I just have my high region A and my lower region D. And of course, that's the entire journey from top to bottom that is given by the battery, right? So region B is gone because B used to be the middle step between the two resistors in series, which I've now combined into one total or equivalent resistance. Okay, so that's combining them. And the whole purpose of combining them is basically you want to get a sense of how much total resistance or equivalent resistance is presented to the entire flow. Now, what we do is we just use Ohm's law to get the total current. So this is Ohm's law applied to the equivalent circuit. If you have a 12-volt battery, that's a 12-volt journey from top to bottom, and you put in its way a collective resistance of 49.33 ohms, then it will inform how much total current will flow. And that total current should come out to be, I'm working in SI units, so this will come out to be in amps, 0.243 amps, or perhaps more handy, talk about, it's 243 milliamps